Alright, so our project was using a sodium carbonate reactor and optimizing the process in producing the sodium carbonate. Sodium carbonate is typically used in industry to soften water and to remove that hardness, and it's especially important in chemical reactions that involve electrolysis, which is used in producing bleach, chlorine, hydrochloric acid, and other products. Our setup involves a semi-batch CSTR reactor that is full of dilute sodium hydroxide to begin with, and then carbon dioxide is bubbled through the reactor. We were able to get the carbon dioxide from two different sources. One is extremely cheap. It is from a cogeneration power plant that is nearby, and it's basically free carbon dioxide in that sense. However, that carbon dioxide is not sufficient for what is needed in the time frame that is necessary to react away the sodium hydroxide. The sodium hydroxide needs to be 80% reacted after 12 hours in order to meet the needs of the industry further downstream from there. And so a Praxair trailer full of liquid carbon dioxide is rented in order to supplement the carbon dioxide from the cogeneration plant. The idea behind our project is that we were wanting to minimize the use of the Praxair trailer but still meet the required specifications in order to produce the sodium carbonate necessary. One interesting design challenge that we had, and this is based off a real-life example, that's where this is coming from, is the measurement device for our reactor is an operator that has a stick with a cup on the end who goes out there, takes a sample, and then titrates it, and then enters that information into the computer, and then our controller adjusts based off that information. So we have a very large time delay from that.
Alright, so in order to model this real life, in order to simulate this real life model, what we did was we took inlet streams. We took the flow from the power plant, we took flow measurement from our Praxair trailer, our temperature from both the power plant and from the liquid CO2 in the trailer, and then we took our ambient temperature and plugged them into a MATLAB S function that models the reactor dynamics in order to get the concentrations of all of the different things in the reactor. However, we can only use the concentration of the sodium hydroxide every 20 minutes in order to control this process. So we made a block, the yellow block sends a signal every 20 minutes to get a concentration measurement from that output of the S function. That's used through the purple block to calculate a rate over the last 20 minutes of reaction. Once we have that rate, then we predict a final concentration based on the amount of time we have left in our 12-hour shift in order to figure out what the final concentration will be if the reactor goes at the rate that it's currently at. We compare that to our set point value and use a P or PI controller to try to adjust the output from the power plant in order to reach exactly what our target value of 80% reacted would be.
So after encoding our project into MATLAB, we went ahead and ran a simple doublet test and fit that to a first order plus dead time model so that we could get the gain and the integral term. We ended up just using a P-only controller, as we found that the integral term ended up it did a poor job of rejecting disturbance, and so the P controller did an excellent job of achieving the concentration that we desired in the amount of time that we needed it to. You can see from this final chart, the top line in red is with the Praxair fully open, and we achieve the concentration, we actually overshoot the concentration that we need in a very short period of time, which also ends up being expensive. The blue line at the bottom, that is with the Praxair fully closed, so we're using only the gas from the cogeneration power plant, and we never achieve the concentration desired in the 12-hour time period that we run the reaction. The green line is our P-only controller, which does an excellent job of hitting the target that we need it to in the 12-hour time period. And lastly, you'll notice the PI control, which also appears to do a very good job of achieving the target that we want. However, when we did the same calculation at night, because of the disturbance of the ambient air temperature, it does actually a very poor job of achieving the concentrations that we need. Thank you very much.